The JADES Deep Field Catalog sorts by luminosity. 3 objects near the top of the list, at redshifts placing them 300 to 500 million years after the Big Bang, sit at the center of one of the most contested interpretive debates in modern astrophysics. Not because the data is wrong. The photometry is clean, the redshift conformation is solid, the observing conditions were nominal. But because 2 competing explanations for what those objects are both fit the data, and they point toward completely different conclusions about the nature of the early universe. The JADES survey team classified them as early galaxies, compact collections of young hot stars forming at rates comparable to the modern Milky Way, consistent with standard models of early cosmic structure formation, stretched but not broken. A separate team of theorists, analyzing the same photometric data, published a different interpretation, that the luminosity profiles, mass-to-light ratios, and spectral signatures of all 3 objects are consistent with a single supermassive object powered not by hydrogen fusion, but by the annihilation of dark matter inside its core. Both interpretations are published in peer-reviewed literature. Neither has been definitively ruled out. The conflict between them is not a footnote. It is the question. Understanding why the dark star interpretation is scientifically serious and not the kind of exotic claim that researchers dismiss on contact requires understanding why the standard model of stellar physics sets a hard limit on how large a star can grow and what exactly dark matter annihilation does differently. The short version is that fusion-powered stars carry the seed of their own destruction in the process that powers them, and dark matter annihilation does not. But that sentence requires unpacking before the JADES anomaly can be felt at the right scale, and the unpacking is where the genuine strangeness lives. Every star in the modern universe is a gravitational compression event. A cloud of hydrogen gas, denser in some regions than others, pulls itself inward under its own gravity. As the cloud contracts, the core heats up. At around 10 million degrees, hydrogen nuclei begin fusing into helium, a reaction that releases energy as photons, as radiation pushing outward against the same gravity pulling inward. The star stabilizes at the point where those 2 forces exactly balance, gravity pushing in, radiation pushing out, equilibrium at every layer. This balance is called hydrostatic equilibrium, and it is what defines a stable star. The upper limit on how massive a star can be before it destroys itself is called the Eddington limit. When a fusion-powered star accumulates enough mass, the radiation pressure from its core becomes so intense that it exceeds the gravitational force holding the outer layers down. The star begins to blow its own material away faster than gravity can recapture it. At around 150 to 300 times the mass of the Sun, fusion-powered stars in the modern universe approach or exceed this limit and become violently unstable. Some explode. Some shed mass continuously until they shrink below the threshold. The Eddington limit is not a theoretical ceiling that clever engineering might bypass. It is a consequence of the physics of photon pressure, and photon pressure is what fusion produces. Dark matter annihilation produces something different. When dark matter particles of sufficient density collide inside a proto-stellar core, they annihilate each other, converting their mass entirely into energy, primarily as heat, without producing the photon flux that drives the Eddington instability. The energy heats the stellar core and provides the outward pressure that prevents gravitational collapse, exactly the same structural role that fusion plays in a normal star, but through a mechanism that does not generate the radiation pressure that sets the upper mass limit. A protostellar object accreting mass in the dense dark matter environment of the early universe, powered by annihilation energy rather than fusion, is not subject to the Eddington limit in the same way. It can keep growing. It can grow to masses and physical dimensions that have no analog in the modern universe, potentially millions of times the mass of the Sun, with a physical diameter larger than the distance from the Sun to Jupiter, as long as the dark matter density inside the core remains sufficient to sustain the annihilation rate that provides the energy. The three JADES objects that a team at Colgate University and the University of Texas at Austin formally identified in 2023, led by Cosmin Illy, Gillian Pauline, and Catherine Fries, published in the Proceedings of the National Academy of Sciences, are JADES GS Z13-0, JADES GS Z12-0, and JADES GS Z11-0. The numerical suffixes encode their redshifts, which translate to cosmic ages of roughly 300 to 400 million years after the Big Bang. The JADES survey team's own classification treats these objects as early compact galaxies, luminous but structurally consistent with dense star-forming regions in an epoch when galaxy formation was rapid and the universe's first heavy elements were only beginning to accumulate. The dark star interpretation does not dispute the photometric data. It disputes the conclusion drawn from it. The team's analysis showed that the photometric and spectral signatures of all three objects are equally consistent, within measurement uncertainty, with a single supermassive dark star rather than a collection of millions of ordinary stars. In a 2025 follow-up paper, the same group added spectroscopic analysis showing that JADES GS Z11-0 and JADES GS Z13-0 remain consistent with a dark star interpretation even at that higher resolution, and identified two additional candidates. The dark star hypothesis survived the contact with higher precision data that might have eliminated it, which is the evidential standard that elevates the hypothesis from speculative to scientifically serious. The population 3 star explanation, as part of the galaxy interpretation, deserves a careful hearing before being set aside because it is the most natural alternative. Population 3 stars are the hypothetical first generation of stars formed from the primordial universe's pure hydrogen and helium. No carbon, no oxygen, no iron, none of the heavier elements that subsequent stellar generations produced through fusion and distributed through supernova explosions. Theoretical models predict that population 3 stars were significantly more massive than modern stars because the cooling mechanisms that cause molecular clouds to fragment into smaller clumps and form lower mass stars require metal atoms that simply did not exist yet. Without those cooling mechanisms, the first collapsing clouds may have formed fewer, larger stars. A very massive population 3 cluster, massive enough to produce the observed luminosity, is a legitimate candidate for any anomalously luminous source in that cosmic epoch. Where the dark star team argues that the galaxy interpretation strains is in the mass-to-light ratios and spectral stability of the candidates. A dense population 3 cluster, massive enough to produce the observed luminosity, would contain stars undergoing rapid evolutionary cycling. Massive stars burning through their fuel in millions of years, going supernova. The cluster's luminosity varying on timescales of millions of years as stellar populations turn over. The JADES candidates show spectral stability inconsistent with this picture. They do not look like objects whose internal energy source is burning through fuel quickly. They look like objects in a stable, sustained energy state, which is exactly what dark matter annihilation provides, as long as the dark matter supply inside the core persists. The galaxy interpretation can accommodate the stability by invoking particular star formation histories and dust geometries. The dark star interpretation accommodates it naturally. That difference is not proof of anything, but it is the reason the two interpretations are still in competition. Active galactic nuclei, the bright cores of galaxies powered by matter falling into supermassive black holes, are the third class of explanation the data must be tested against. Quasars and other AGN can produce luminosities comparable to what the JADES objects show. They are also variable. The accretion process that powers them is turbulent, and AGN brightness fluctuates on observable timescales. The JADES candidates do not show this variability. Their spectral signatures also lack the characteristic emission line ratios that AGN produce when accreting material heats to temperatures that excite specific atomic transitions. The AGN explanation is inconsistent with the spectral data across both the 2023 photometric analysis and the 2025 spectroscopic follow-up. Removing AGN from the list of viable explanations narrows the competition to the galaxy interpretation and the dark star interpretation, two explanations that are currently indistinguishable from each other at the precision of available data, and that require fundamentally different physics to be true. Dark matter has been inferred gravitationally in every galaxy survey conducted since Vera Rubin's rotation curve measurements in the 1970s. Galaxies rotate as if they contain far more mass than their visible stars and gas account for, and the best explanation for that excess mass is a distributed, invisible component that interacts with ordinary matter only through gravity. Every direct detection experiment designed to catch dark matter particles interacting with ordinary matter through any other force has returned a null result. The Large Underground Xenon experiment, the Panda X detector in China, the Xenon NT detector in Italy, all null results, at sensitivities that rule out large portions of the theoretical parameter space where dark matter particles were expected to be found. Dark matter as a concept has been confirmed gravitationally and refused to appear in every other experimental context. Dark stars, if confirmed, would require dark matter to have an annihilation interaction cross-section, a measure of how likely dark matter particles are to encounter and annihilate when they encounter each other, large enough to power stellar mass energy production. That cross-section is many orders of magnitude larger than what current direct detection experiments constrain for the dark matter candidates they are designed to find. The conflict between what dark stars need and what direct detection experiments rule out points in one of two directions. Either the direct detection experiments are missing the signal because they are looking for the wrong kind of dark matter candidate, or the dark matter that powered dark stars in the early universe is a different phase or component of dark matter than what dominates today, present at higher density and annihilation rate in the extreme environments of the first few 100 million years, and since diluted or decayed to undetectable levels in the modern universe. Neither resolution is comfortable. Both are testable in principle. The pathway to confirmation runs through spectroscopy and mass measurement. The key observational distinction between a single supermassive dark star and an unresolved galaxy of population 3 stars is the absorption line pattern in detailed spectroscopy. A single massive object produces a different pattern than a collection of objects at different temperatures and evolutionary states. The 2025 spectroscopic analysis identified a tentative He2 lambda 1640 absorption feature in JADES Z1403 that the dark star team describes as a potential smoking gun signature. That identification is preliminary. It requires confirmation at higher signal-to-noise. Webb's NIR SPECT instrument is capable of the required spectroscopic resolution for objects at these redshifts, but the integration times required are long, the targets are faint, and the competition for Webb observation time is intense. Gravitational lensing provides a complementary path. If a massive foreground galaxy or cluster happens to lie between Earth and one of the JADES candidates, it can magnify the candidate's light and allow higher signal-to-noise spectroscopy than would otherwise be achievable. These lensing alignments are not controllable. They either exist or they do not. But the JADES survey area is large enough that the probability of finding useful lensing geometries for some of the anomalous sources is non-negligible. The secondary implication, the one that matters for cosmology beyond stellar physics, is that dark stars provide a formation pathway for supermassive black holes that standard models lack. The existence of quasars, 1 billion times more massive than the Sun, observed in galaxies when the universe was less than 1 billion years old, is one of the persistent puzzles of observational cosmology. Standard black hole formation, stellar core collapse producing a black hole of tens of solar masses, followed by gradual accretion, does not produce billion solar mass black holes fast enough to account for what quasar surveys observe. A dark star that grows to 1 million solar masses and then transitions to fusion-powered burning when its dark matter supply is exhausted, or collapses directly when the annihilation energy drops below what is needed to support the stellar structure, would produce a seed black hole of a mass that standard accretion can grow to quasar scale within the available time. Dark stars as the origin of every supermassive black hole in the observable universe is not a fringe proposal. It is a logical consequence of the dark star hypothesis that astrophysicists are actively working through. The three JADES candidates are 3 data points. 3 is not a population. It is not a statistical sample. It is the beginning of a catalog that either grows as more Webb observation time confirms the pattern across additional objects, or stalls as higher resolution data reveals that the galaxy interpretation accommodates the evidence more naturally than the dark star alternative. Science at this stage is provisional in the most honest sense. The dark star hypothesis is consistent with current data for 3 specific objects. It is published in peer-reviewed literature at the photometric and spectroscopic level. It has not been refuted, and it has not been confirmed. The researchers who published it said exactly that. What is not provisional is the question the objects pose. Something is at those coordinates in the early universe. Something produced the luminosity and spectral signature that the JADES survey recorded. Whether that something is a compact galaxy of the earliest stars, consistent with standard cosmological models pushed to their early universe limits, or a single supermassive object powered by the annihilation of dark matter, consistent with a theoretical framework that has been developing since 2008 and now has survived 2 rounds of increasingly precise observational testing, is the question the available data cannot yet answer. The universe at 300 million years old was a different place than the universe now. Dark matter was denser, concentrated in the first collapsing structures, not yet diluted by 13 billion years of cosmic expansion. If dark matter annihilation can power a stellar object under those conditions, and the physics does not prohibit it, it only requires sufficient density, then the largest objects in the history of the early universe may have been powered not by hydrogen burning in nuclear fire, but by something burning in dark matter, before anything we recognize as a galaxy or a black hole or a heavy element existed. Webb found the candidates. The spectroscopy is ongoing. The answer is not yet in.